So we're still looking at position vectors and also how to get the component along an axis. So we'll still be demonstrating those techniques. In this case, we have this question that was shared by Kangwa. And what they're saying is, determine the angle theta and the angle phi made between the axis OA and the flagpole AB and AC. So here, of course, OA is the flagpole. They want us to find the angles between the flagpole and AB, and also the angle between the flagpole and AC. So I have two questions. In the first part, we want theta. In the second part, we want phi. Now, how do we approach that? Well, let's say the first part, let's look at between OA and that's AB and AB. So I moved this one up, okay, and AB. So after that, we're going to look at OA and AC. Now, once we know what we're trying to do, the next part is how do we get the answers? How do we get the angle between them? Well, there are several ways you can actually get angles between two lines. Among them, the methods that you guys have looked at so far, you've looked at, if you know, let's say, your vectors very well. If, let's say, you wanted to find the angle between this line, that is this line here, let me just sketch through it. If you wanted to find the angle between this line AB and the line OA, OA is here. OA is here. So if you wanted to find the angle between them, among the things you would need, first, you would need to know this side, which is from here to there. You'd have to know what this is. You'd have to know what this is. Maybe you might be able to predict what the angle between them would be, but it's going to be very difficult for you to actually achieve this. It's worse because if maybe B was right above this point, if B was maybe right above this point, maybe then it would have been easier. But you see, to say B is not right there, B is actually displaced a little bit this side. So which makes it a little bit more complicated. Because if it was strictly vertical above O, you'd have said that this vertical line is also the same as 6. So we can't use the direct method of just getting angles, or maybe even that shortcut we saw of using sine and cosine to get angles. In this case, those are going to be a little bit too complicated to employ. So instead of using those techniques, we're going to resort to the dot product, which we have seen in recent examples that it's actually very efficient to use, especially for questions like this. But if we're going to use the dot product to get an angle between two vectors, what do we need? Then we need the vectors themselves. So I can say, here we can say force vectors or position vectors. But even if it's, do they want a component? They don't want a component. They just want an angle between them. So they don't need necessarily the components themselves. So if we can get the displacement vector, from, let's say, ROA, and also get the displacement vector RAB, and also get the displacement vector RAC. If we can get these three vectors, to get the angle between ROA and RAB, you know to say the dot product between any two vectors, ROA dot RAB, the dot product will be the same as the magnitude of ROA multiplying the magnitude of RAB, then cos the angle between them. You remember this relationship. I think it's, we looked at it in some examples back. So this is one other property of dot product. We sort of say you can use it to find a component. Now we're seeing how we can use dot product to find an angle between two vectors. So for this example, this is the relationship that we're going to use. I'm seeing the question was actually giving us what the forces are, since we know what FC is, and we're also given what FB is. So my conclusion from this is that maybe there was a follow-up question that is not part of this. There probably was a follow-up question that was also referring to the diagram where maybe we had to get a component of the force in some direction. That is why they were giving us these forces. But for this question that was shared, we are only looking for AB and AC. No, the angles between OA and AB and the angle between OA and AC. So for now, don't get confused with those forces. For now, we don't need the forces. We only need a vector running from O to A and a vector running from A to B. So there will be no need for us to get the force in vector form. So I hope that is clear. So with that in mind, we only need the position vectors themselves. Once we have the position vectors, there'll be no need for us to even deal with unit vectors. This is going to be much, much straightforward. With that out of the way, let's get the position vectors. Let's start with R running from O to A. How do we have to move here? Well, the origin is positioned way at the bottom here. So the origin is positioned here. We have to move from O to A. What you have to see here is A is actually literally right above the y-axis. A is literally right above the y-axis. What does that tell us? Since A is above the y-axis, it kind of tells us to say that to reach A, there will be no displacement in this direction. We do get to go up, meaning there will be a Z component, but we don't get to move in the x-axis to reach point A. So to move from O to A, we are not going to have an X component. So since X component, we have to get displacement in the X-axis or in the horizontal axis, because it's weird to say horizontal here. So let me just say we are not getting any displacement in the X-axis. So of course, again, I was able to see that based on the fact that if you look at this part, they're saying that the point A here is literally right above the y-axis. They're drawing it right above the y-axis. If they wanted to show us that this is not above the y-axis, they might have done something that looks like this. They might maybe have sketched something. We can put it up to where? We can say they might have sketched it maybe up to somewhere like this, and then put our 3 somewhere here. And then also maybe give us what this is. Notice that if they had done this, they would have told us to say that, well, to reach point A, you probably have to, maybe they would have even put it somewhere here so that you go like this first, then you go up to reach that. Then we are seeing there's a displacement in the horizontal axis, if this was the case. But it's not the case. The way it is, we are not having any displacement in the x-axis to reach point A. So let's see our position vector. To run from O to A, how do we move? In the x-axis, we don't move altogether, so that's a 0. In the y-axis, we're moving along the positive y until when you reach this point. And based on this line, this 4 meters that is at the bottom, you have to see that from this point, from O, to reach this mark here, this line, don't confuse it with this. This line is actually to show us that to reach this end of this arrow here, this is what they're trying to show us. That's a 4 meters. So in the y-axis, you're actually getting to move 4 meters in the positive y. So we have a 4, y is denoted by the unit vector j. And then next, how about in the z? In the z, we see that in the z, we have to go up from this point until when we reach point A. Notice that just by doing this, we would have reached our point A. And how far up? Denoted by this, that is 3 meters up. So that is again along the positive z. So this is going to be plus 3k to show that we're in the z. So this is our OA. Any questions there? Okay, looks like we're okay up to that point. Next, we need our, let's say, AB. The position vector running from A to B. How do we move in this case? Well, from A to B, So I'm going to remove OA. Let's just concentrate on AB. How do we move to reach B? Well, for this one, you have to be a little bit more attentive. First and foremost, based on this part, maybe I should even use positions as in coordinates of each point. For this one, I think it's wiser to use coordinates. So let's look at the coordinate of the point B. The coordinates could have also worked on the first one, but it was easier to just follow it by just tracing the movements. We can trace the movements here, but if I'm going to explain it better, let me just show you the coordinates. Let's start with the coordinate of the point B. The point B, to reach the point B, look at what you have to do. In the X, you have to displace by this much. How far do you have to go? We see that to reach not all the way up to there, it's literally just this one. So it's like in the X, it's just coming up to like somewhere here. And based on this, in the X, you have to go 1.5 meters. And that is in the positive X. So that is in the positive X, that is 1.5 meters in the positive X. So what else? In the Y, what are you doing in the Y? So when you observe this, the point B is literally along, it's above the Y, the X axis. So it's like we have the X axis being here. And then the point B is literally above the X axis. So being above the X axis implies that to reach the point B, you don't move anywhere in the Y. You don't go to the positive Y. You don't go to the negative Y. So in this case, we're trying to say that in the Y axis, you don't go anywhere to reach B. So that's a 0. Then in the Z, you have to go all the way up. And based on this, you have to go 6 meters up in the Z. So you have the 6 meters here. So we have the coordinates for the point B. How about for the point A? Well, for the point A, let's see what we have to do. For the point A, it's similar to ROA since O is the origin. For the point O, that's A, I mean, you have to move from O. In the Y-axis, you're coming up to this point. And remember, we saw that's a 4. In the X-axis, you don't go anywhere for the point O, for the point A, I mean. So that's a 0 in the X, a 4 in the Y, and then in the Z, again, remember, you had to go up 3 units up. That's 3 up in the Z. So these are the coordinates of the point A. So to move from A to B, remember how it goes? It's the final point minus the initial point. So since you're moving from A to B, so the final point is B. So it's going to be the coordinate of B minus the coordinate of A. So for B, in the X, we have 1.5. For A, we have 0. So this is going to be 1.5 minus 0. This is in the X-axis. Plus, in the Y-axis, the final point again is at B. So the final is at B. The initial is at A. So the final in the Y, that's a 0 at B. And that's a 4 at A. So that's a 0 minus 4. This is in the Y-axis. Plus, how about in the Z-axis? In the Z-axis, we have to go up. So let's start with the final. The final is 6. The initial is 3. So we have 6 minus 3. That's a 6 minus 3. Okay, so this is what we have. So just simplify this. 1.5 I minus 4 J. Then this becomes plus 3K. This becomes the position vector from A to B. Having done this, we can now easily evaluate what the angle between ROB and RAB. So to get that, all we'll do is evaluate the dot product. Let's say, doesn't matter the order, OA, RAB, this has to be equal to the magnitude OA, RAB, then cos the angle between them. So what's the angle between these two? For these two, the angle in question is this one, and they've labeled it as theta. So we're going to have a theta there. So from here, we're seeing that we can try to make cos theta subject. Cos theta becomes equal to the dot product, or this is the dot product. Then divided by the magnitude. So that in the end, we just have cos inverse here. So theta will be cos inverse of this ROA dot RAB, then over their magnitudes, ROA and then RAB. So you can evaluate everything right by plugging them all here, or you can do them even in steps. So let's get the magnitudes first. So let's say the magnitude of ROA. What do we need? For ROA, remember it's 0, then 4, then 3. So that's just 4 and 3. So that is going to be the square root of the x component, which is a 0, so we'll skip it, the y component, which is a 4 squared, plus the z component, which is a 3 squared. So that in the end, this is the square root of 16 plus 9, which is the square root of 25, and the square root of 25 is just a 5. So that is the magnitude of ROA. Next, the magnitude of RAB. For RAB, what do we have? RAB, we had 1.5, 4, then a 3. No, is this the one? Yes, that's the one. 1.5, 4, then 3. So let's see how it goes. That's 1.5 squared plus, notice that the next one is a minus 4. It won't really matter since it's going to be squared. So just don't forget the minus is there. Then you square everything, including the minus. Then the last one is a 3 going up. So this is what you have to evaluate. So what is this giving you? What are we getting here? What point? You say 45.22? 5.22. Okay, so these are in meters. Even this was in meters because the coordinates were, the displacements were given in meters there as well. So we now have the magnitudes. The next thing that we can get, yes, please.
I'm finding 6.02.
6.02.
Uh-huh.
Okay, can you guys verify 6.02, which is which?
6.02.
Okay, so 6.02. Okay, so the next thing that we can get, we can also evaluate the dot product, ROA dot RAB. So you know how the dot product goes. The first one is, that's 4i, or 4j I mean, plus 3k. Then dot, the second one is 1.5 I minus 5j plus 3k. So the dot product here is like for like. In the first part, there's no I. So for I, we have a 0. So it's going to be 0. So if I was to write everything, this is 0 times 1.5. That's just going to be 0. Plus, next we have the j term. For the first bracket, we have a 4 coming from j. And then for the second one, we have a negative 5 coming from j. And then j dot j again, that's a 1. Next, we have plus the k values. That's 3, and that's a 3 there as well. So we have 3 multiplying 3. And then again, k dot k will give us a 0, a 1, I mean. So again, dot product, it's always like for like. Cross product, the like for like always disappear. We only have the different ones. Okay, so we'll see. We've seen cross product for the other guys. So for those who haven't yet, we'll still get to it. So the first one will just be a 0. The next one is 4 by 5. That's minus 20. Plus, then we have 3 by 3. That's a 9. So we're seeing that the dot product here is just the sum here, which is minus 11. Is that okay? Okay. So remember what we had? Theta was equal to cos inverse of the dot product ROA dot RAB. So I should be going through what I'm doing just in case. And then we have ROA. And then we have RAB. This is what we had. Now we know everything here. The dot product, remember we just ended up with minus 11 as the dot product. Now the magnitudes, the first one was a 5. So we have 5 here. Times the second one was a 6.02. So the second was a 6.02. So let's evaluate this. What are we getting?
111.4 degrees.
Like this?
Yes.
Okay. So this is the angle that we are finding there. Let's look at it. Okay, yeah, that's what we're getting there. Is that okay? Sylvester? For A. ROA. ROA is there's no 5. Or how did you end up with the 5? We ended up with the, yes, please. Where? 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 RAB. I'll put -4. -4. This one.
Yes, but in the calculation put -5.
In the calculations will put yes. This one, huh? Yeah, this is -4. Right?
Yes, it's -4.
Okay. So let's make those adjustments. I'll come back to the question that we were getting earlier on. This becomes what? What's that? Okay. Yeah, that changes a few things. This is still okay. I think it changes this one because we also use the 5 here, which is a 4. So that means this is a 4 here as well. That's the J term. So that the J term, which is this one, is now -16. -16 by 9, -16 plus 9. This now becomes plus, is it 7? -7, I mean. So from here, now we have -7 here being divided by, this is not this, this is 5.22. What is this becoming now? What's that? 105.5. Okay, so I hope everything is okay from here. There's another question. How did we get?
You answered the question. I was just surprised how we got that.
That 5. No. There's no 5 there. I think it was just I don't know how I ended up writing 5 there, but there was no 5. As you can see from everywhere else, I think the calculation, there was no 5. This gave a -4. I don't know how I ended up writing -5 there. Okay, so are we okay here? So we can now move on to the next part. For the next part, they now want us to get the angle between ROA and that's AC. So we're going to take advantage of these position vectors. So we already have our OA. All we need is our AC. For AC, let's get the coordinates of the point C. And let's see, can you guys tell me the coordinates for the point C? Look at the diagram. What do we have? So we have -2 in the x-axis, yes. What else? 0 in the y, yes, that's 0 in the y. And in the z, +4, yes, we go up in the z. So those are the coordinates. So to get our AC, we're going to have, again, we are moving from A to C. So the final is -2. So we're going to have -2, -0 in the I, and then plus the final is 0, minus in the y, the initial is 4. And then in the, this is J, and then in the Z, our final is 4. Our starting point is from 3. So we're going to have -3. This is K. Pardon? You've seen it? Okay. Okay, so we have RAC. In the end, this will be -2I, and then -4J. Then this is going to be plus K, because 4 minus 3 will just be 1. So that's plus K. So this is what we end up with as RAC. So remember, we already have what ROA is. Let's just bring it here so that we get them together. ROA, that was 0 in the I. Then we had, now what else was there? 4J and 3K. So that's 4J and 3K. So this is what we had. This is what we're going to deal with. So let's get these. Now let's find the angle between these vectors. Okay, now to get the angle between them, again, we're still going to use the same approach. We'll go right ahead and say the angle between them. Now that angle is labeled as phi. This is going to be cos inverse of the dot product of AC. And again, the order doesn't matter here. And OA divided by their magnitude. That's OA there. So this is what we are evaluating. So let's get let's get the dot product. So for the dot product, that's RAC dot ROA. So the RAC, that's -2 minus 4 and 1, -2 minus 4 and 1 dot. Then that's 4J plus 3K. So you can put 0I if you want, but that's okay if you just remember that I has a 0 there. So 2 multiply the 0 for I, we can even leave it out. And then -4 will multiply the 4. Then plus the K will multiply the 3. So that's just 1 by 3. So again, it's like for like, the thing with the K multiplies the coefficient of the K the other side again. So in the end, we have -16 plus 3. And this comes to give us -13. I hope you guys are following. So we now have the dot product. Now we need the magnitudes. We already have the magnitude of ROA. We found it earlier on. ROA, what did we get? ROA was, that was 5, huh? That was 5. ROA was 5. So we'll still use it, 5. But all we need is RAC. RSC is going to be the square root of, the first term is -2. Don't forget the minus also has to be squared, plus the y is -4 again, plus the z, that's just the 1. So when you simplify this, we have √4 plus 16 plus 1. So that's a 20 here, a 21 there. So this is √21. So in the end, what we're evaluating here is cos inverse of the dot product. We had -13. You guys can verify that. -13. Then over RSC. RSC is √21. You can get it in decimal. Then multiplying ROA, which is 5. So what are we getting here? 124.5. So this becomes the angle in question. Okay, so do we have any questions here?